Welcome to a lesson with Dr. Powell. In this video, let's take a look at something I call sign determining polynomials to figure out where a derivative, see this is f prime, is positive or negative, where the output of the derivative itself is going to be a positive output. So when graphed above the x-axis, or it's negative below the x-axis, and that's going to help us know where the actual function is going uphill or downhill rather quickly. And we're going to do this with when the derivatives are in kind of a nice factored or fraction form, factored fraction form, if it isn't a fraction perhaps, or here it's just factored. And the way we're going to do that is, so from one part to another, see how this is multiplied, we're going to look at the graphs of each part. So the graph of this part, e to the x minus 1, if you think about an exponential graph, it's increasing. And where does it hit the x-axis? When is the output equal to 0? Well, in this particular case, when x is 0, that's going to make it work, right? 1 minus 1 is 0. So it's going to behave a lot like, and you think about a polynomial that does the same thing with signs. So if you can think of a polynomial that does the same things with signs along the way, that's helpful. So here, this is kind of like the polynomial y equals x. Like that, the graph, or this expression right here, a function equal to that expression as an output, it will have the same sign behavior as e to the x minus 1. Of course, this guy's already a polynomial. So then what we do is we just simply think of this as being negative x squared times x. In other words, negative x cubed. What does negative x cubed look like? Well, x cubed looks like this, so negative x cubed looks like that at 0. So it looks like this is a polynomial negative x cubed, and it looks like this, which means, you're thinking about it, on this side of 0, it's going to be positive. On this side of 0, the output is going to be negative. So the derivative is going to be positive to the left of 0 and negative to the right of 0. So the original function, f of x, is going to be going uphill to the left of 0 and downhill to the right of 0. So it's going to peak out right there at 0, and we'd end up having a maximum. If we take a look at this and think, when we plug x equals 0 into the derivative itself, notice we've got 0 times 0. I mean, we're going to get 0. So we're going to have a instantaneous flattening right there. So the graph's going to flatten right there and have a maximum there. Of course, it's going to be going downhill. Now, it's going to be going downhill till this endpoint of the interval. So we're going to graph this, or thinking of the graph just on this closed interval of the original function, f of x. You know it's going to max out at x equals 0, and then as it heads downhill, it's going to get down to x equals 5, and then it's going to be coming up from x equals negative 3, going uphill from that point. So these 2 points will actually be minimas, or local minimas. Locally nearby, this point will be a minimum, that will be a minimum. Which one will win out in this interval to become the global maximum of, or minimum, that is, on that interval? Well, you have to plug in negative 3 and 5 individually into here to check to see which one will be the lowest. But this one will definitely be global maximum, because, looking at the quick sketch, that'll be the highest point at x equals 0. Keep in mind that what is being maximized and minimized is actually the y value, not the x value. So, when we're saying, what is the local max? Don't say x is equal to 0, or global max. Don't say x equals 0. We got to plug in the 0. When you plug in into the original function, I don't even have the original function here. We can't even figure this out right now, can we? No, we can't. Okay, it's because I did not give you the original function in this particular video. So f of x is equal to What? Yeah, you don't know. So you'd have to plug in x equals 0 into the original function, so f of 0, to find the y value there. And then x equals 5, you'd have to plug in to find that guy and the actual minimum there and minimum there, and then you compare the two. But in this video, I'm not showing you that. That's not what I'm focusing on. I'm just focusing on getting the behavior from a sign determining polynomial. All right, we're going to go on to another example here and kind of keep us moving along. So right here, do the same type of thing. Now, notice, all right, let's take a look at this guy right here. This exponent, 4/5. So it's like you're taking a fifth root and then you're raising it to the fourth power. So a fifth root, or an odd root, does not change the sign of anything, so it can be ignored. So really, we're only focusing on this numerator. Now, a fourth power, that does the same thing as just squaring an even power there. So any even power you could just replace with a 2. And then, it's in the denominator, right? But moving from the denominator to the numerator doesn't make a difference. You could just do it with signs, whether something's positive or negative. Remember, we're focusing on what makes things positive or negative. Moving from the denominator to numerator does not change that idea at all. Maybe it changes things when, or is critical when at a critical point where things blow up or something like, x equals 1 or whatever. But we're not doing that right here. We're away from that. We're just looking for things in between. We're not so like in the last example, we were not focusing at 0. We're just going away from 0. Same thing here as we proceed. So our polynomial, our sign determining polynomial, is actually negative quantity x minus 3 times x minus 1 squared. That'll give us our signs. If you look at my videos, which talk about how to graph polynomials sketches, that's what I'm going to be using here. Leading term of this. Take the leading term of each factor. Negative 1 is leading term of that guy. X there. And here I have 2 x minus 1's, leading term of x 2 times over. X times x times x times negative 1, that's negative x cubed. Negative x cubed will look like, it's the same thing as we had last time, right? It'll look like this. All right, so for n behavior, but we're hitting the x-axis at different places. We're going to be hitting it, when is this expression equal to 0? At 1 and at 3. It's going to start up, going to end down, and how is it going to hit each thing? As it hits the 1, you see x minus 1 right here, where this one came from, has a little 2 right here. That exponent's even. That means that we're going to have a bounce. Now, next time we hit the x-axis, we're going to hit this 3. How are we going to hit it? See, this guy has a 1. It means it's going to shoot through. Notice it has the proper end behavior from up to down. So this gives us a sign chart for our first derivative. We're going to have positive, positive, negative. All right, so that means our original function is going to be going uphill to x equals 1, and then uphill again to x equals 3. And then beyond there, it's going to be going downhill. So we know we kind of have this rough schematic. Now, specifically at x equals 1, what is the function going to be doing in terms of slope? Because we have the derivative, which tells us what's happening with the slope. If we plug in x equals 1 into here, oh no, blowing up, something infinite, right? We're getting toward, as x gets close to 1, we're going to be getting something infinite coming out of the derivative. But I'm going to give you one other thing on this. Let's assume that f of x is continuous, which this actually does come from a continuous function example, but I'm just not giving you the formula for it. So if f of x is continuous, then, okay, so everything's going to connect. Okay, but the derivative is infinite. Well, let's think. The derivative is positive here, and kind of, it's going to be infinite here, positive infinite here, because it's positive. Like, as we're heading toward 1 here, it's heading toward a positive infinite slope, and away a positive infinite slope. So it's going to look like, kind of like a vertical tangent is what we're going to get here. So as we're coming up vertical tangent, that's what that means. So we're going to get a vertical tangent right here at x equals 1. At x equals 3, if we plug in 3, notice the derivative is going to be 0 momentarily. We're going to get a momentarily flattening at x equals 3 and then coming down. So that we get some nice information here at x equals 1 from a sign determining polynomial of the first derivative. And we'll move on to another example. Here, same idea. So this on this interval, if you were to graph it or look just at the natural log part, it'll be like an x minus 7. I mean, how could you do that? I mean, you could think about the natural log function as simply being, let's see, you could think of the natural log function. If you know what the graph of it looks like, you know it's like increasing like this. I mean, this has been shifted in some way. Where is this going to be equal to 0? It's precisely when the input of the natural log is equal to 1. Where is it equal to 1? Well, if you put in an x equals 7 here, you're going to 7/12 and 5/12, it's going to give you a 1. So, I mean, you think it's going to be like this. It's just been shifted, no reflections or anything. And so, really, yeah, it's going to hit the axis at x equals 7. That's like the polynomial x minus 7 that we can use for that whole guy. Kind of nice there. So our whole polynomial is going to be negative x minus 3 times x minus 7. All right, end behavior, x and a negative x squared, going down, down, down. Where's it going to hit the x-axis? At 3 and 7, 3, 7. You have a minus, plus, minus function, original function, going downhill, then uphill, then downhill. We got all of that just from that, quickly noticing that. All right, so original function going down, then up, then down. Pay attention to what's happening right at 3 and right at 7. So at 3, when we plug in 3, it looks like we're going to be getting out a 0. When we're plugging in 7, we're going to get an ln of 1, which is 0. So we're going to, these are going to be flattening points. That's kind of nice. So flatten and then flatten. Now at the endpoints, of course, you know, this endpoint is going to be actually, this ln function is actually well defined on the interval. You can check it, and you're going to have exactly what you want there. So the interested viewer can check that out. But this is actually going to, so at this endpoint you'll have a max, this endpoint you'll have a min, this one you'll have a, these are local maxes and mins. You'd have to check the y values to see if they are globals, but I didn't give you the function again. So, so we can't really in this particular example, but that's theoretically how you would do that. But at least we know there are local maxes and mins. All right, and one more. Let's take a look at this cosine graph. Ooh, well, actually, if you look at this and you think about how the cosine graph shifts and so forth, it's actually going to hit the, it actually looks a lot like we're looking at a piece of it from -1 to 3, and we're going to be hitting at 0 and 2. The interested viewer can actually go ahead and check out that little piece to verify that. But assuming on this interval, and it doesn't, and it'll look exactly like this, it won't come back to the x-axis anywhere. So we can, our polynomial that looks like that graph is this. So that's the part we'll use with the negative x cubed and multiply it through to become negative x to the 4th times x minus 2. And then we look at the end behavior of this, negative x to the 4th and times an x, so negative x to the 5th, which looks something like this end behavior-wise. So we start up and we end down, be hitting the x-axis at 0 and 2. How do we hit it at 0? Looks like with a bounce. It's even. I mean, we could have made that a 2, but whatever. Let's see, with a bounce, so at 0, so it's going to bounce there, and then it's going to shoot through it too. So meaning we're going to have positive, positive, negative. All right, so our function, original function, is going to be going uphill to x equals 0, and then uphill again to x equals 2, and then it'll be going downhill beyond that. So what happens specifically at 0 and 2? So we would plug in x equals 0 into the derivative to notice that, well, we're going to get 0, yeah, and this is just a nice number, so it's going to be a flattening there. It's going to be like a saddle point, flatten and then up, okay, momentarily right there. What about at x equals 2? So let's see, at x equals 2, if you plug that in, note this part will give you a 0. I mean, you can check that. You'll get cosine of 3 pi halves, yes, is 0. So the whole thing is 0, so it's flattening as well. So we're going to get, so as we go up, it's going to come up, flatten at x equals 0, come up, flatten momentarily at x equals 2, and go back down. So on this interval, we'll be looking at something like this. A min, a saddle, a max, and this other endpoint will also be a minimum. Okay. I hope you gleaned something from these examples, and thanks for watching.